Well, hi everybody. Hope you're all doing well. I've got another little instalment for you today in the area of differential calculus, and it's the amazing area of related rates. Some students might say related hates, but after I'm finished with them, they will be your mates, okay? And you'll really be happy, just like this little guy here. So, related rates. It's a very exciting, very interesting area, and let's have a look at it. We've got a great big inverted cone here, and this is a favourite area for exam questions. In fact, there was one question a few years ago which got labelled the cone of death because nobody seemed to be able to do the question. So we'll just put an end to that. So this cone here, you can see it's an inverted cone, and you can see the dimensions of it, radius 10 and 30 centimetres deep. But we're actually, when we start this question, the cone is actually empty, okay? And what we're going to do is we're going to run some water or some liquid through a tap at the top, and that's basically liquid pouring in at a steady flow rate of 2 cubic centimetres per second, okay? That's the deal. And the question that we have to answer is, what is dh dt? That is the height of liquid in the cone at the situation when h is 5 centimetres, okay? So that's exactly half the, oh no, it isn't 5 centimetres, that's 1/6 of the possible height that you could get for a 30 centimetre high cone. All right, let's have a go. Now, I'm going to define the term here, let V equal the volume of liquid in the cone at any time t seconds after the liquid starts pouring in, and that would be in cubic centimetres. So I've defined my terms now because we weren't given any pronumerals in this question as such. So now I feel happy. I've got, well, at least we have R and H defined, but not V. Alright, so what's next? So I want you to ask yourself the question. This is the systematic way that I've worked out to do these sort of kinds of questions. What rate do we know? In other words, what rate have we been given a numerical value for? Think about that, because that is where you start this question. Now, I happen to know that the flow rate of liquid into this cone is 2 cubic centimetres per second. So with a volume of V of liquid in there, that would be, what derivative would that be? What rate with respect to this, in this case, time? Yes, it would be dV dt. Okay, the rate of change of volume with time is plus 2 cubic centimetres per second. So that's where we're going to start. That's going to be the left-hand side of an equation we're going to form. Okay, a chain rule equation we're going to form about related rates, not related hates, related rates. And that's dV dt is 2 cubic centimetres per second, right? Now, the second question you ask yourself is, what rate do we want? In other words, what are we asked for? Well, we're asked for dh dt, aren't we? See the purple bit up the top of the page? And that's when h is 5 centimetres. Okay, now that's all you need to set up our related rates equation, right? So it goes, yes, that's dh dt. Now, here's your equation, guys. We say that dV dt, and that's on the left-hand side, is equal to dV d something times d something dt, okay? Now, the question for you and for me is, what is that something? What is the something, okay? Now, so we want to know what goes in the blank. Well, have a look at the line above, you guys. What do you see in that little red circle? That is the answer to our puzzle. Okay, so dH goes in there, and that is a chain rule expression, all right? That is a chain rule expression. So if you have a look at that, we've set it up. And that's the way you do it every single time. No more confusion necessary, okay? It's chain rule. So that's the one we know. We've been given that. That's the one we started with, remember? and this one on the right is what we want, that's what we're asked for, so that has to be featuring in the equation, and this second one is the one we need but so far haven't got. So the bulk of this question, apart from just setting up the equation there, the bulk of this question is about setting up the relationship between v and h so you can then take its derivative. And once you've done that, everything falls into place. Now, there's a little bit of complication with getting the relationship between v and h, but it's not that complicated. I'm going to turn the cone of death into the cone of easy for you, okay? Just watch this. We know that v is 1/3 of pi times r squared times h. Now I hope you know that, because that's the formula for the volume of a cone. 1/3 of the volume of the base times the height. Now remember, in this case I'm talking about the volume of liquid in the cone, right? Not the volume of the cone shell itself. We're talking about the liquid here, okay? A dynamic situation which changes from one moment to the next. Now, we've got our formula, haven't we? So shouldn't we be able to do dv dh now? There's a problem. There is a problem. And that is that r and h are both variables and are both connected. Yes, they're both connected. In fact, r is actually a function of h. You can express r in terms of h. So therefore, that r is actually a little bit of h in disguise. That's what I'm saying. So we have to sort that out. We have to get the relationship between r and h and then use that to express r in terms of h in that expression one line above where we are now. Okay? Now don't worry, I'm going to show you how to do it. It's really easy, okay? Here we go. So r is truly affected by h, so that's no good. We can't have that. We've got to basically just have the one variable in the expression on the right hand side of that green equation, so we can, and it's got to be h. Okay, so then we can take dv dh and everything will become roses. Okay, all right, next screen. Now we got to there, didn't we? Right. Now how do we get the relationship between r and h? Well, it's very easy. What do we need? Yes, we need one variable, Mr. Computer, thank you so much, and that's h for dv dh. Now, check this out. How are they connected? Well, you might ask. I'm going to show you. Now, it's all about similar triangles, okay? Similar triangles. See that triangle above there? That basically represents some dimensions in that cone. Now you can see the 10 centimetres across the top, which is the radius. We see the 30 centimetres down the left hand side, which corresponds to the depth of the cone. And we've got r, which represents where the level of the liquid is at that point, about halfway up the diagram, okay? Horizontal. That's the r of the actual surface of liquid which is built up, the volume of liquid which is built up in that cone. Now, there's h. H is the height of liquid in the cone. Now, these triangles, I'm going to put some letters on them, A, B, C, D, E. Now, what I'm saying to you guys is this, that in triangles A, B, E, the big one, and C, D, E, the little one, okay, I'm going to prove they're similar. Now, you won't have to prove this in an exam setting, but I'm going to prove it to you so you'll know why I'm now allowed to use, after we prove it, we'll be allowed to use, mathematically speaking, allowed to use ratios to sort out the relationship between h and r. Okay, you see that little dot angle I've got down there at the very bottom vertex of that diagram? That little dot, that's angle. That angle is in common to both the little triangle CDE and the big triangle ABE. So that's a common angle, isn't it? It is. Right. Now, what else can I say? Those angles I've just labelled on the left, they're corresponding angles because of those two parallel lines, horizontal lines, AB and CD. So they are the same angle. And thirdly, those green angles on the right, they are also corresponding angles because of those parallel lines, AB and CD. So therefore, guys, triangle ABE is similar to triangle CDE bracket AAA. In other words, all three angles. They're equiangular. So therefore, what does that mean? It means that the two triangles are scale models of one another. One is just a scaled up version of the other. So therefore, we're quite entitled to use ratios on corresponding sides because they are scale models of each other. So what does that mean? We can then say, yeah, the corresponding sides have the same ratio. So I'm going to draw a little equation up now. Therefore, R over H would be the same ratio as in the big triangle, the 10 horizontal over the vertical 30. Good grief. So what does that tell us? It tells us that R is H over 3. My goodness, that is so important we put a box around it, okay? And now that means that's our ticket to putting R equals H over 3 in that green expression on the left, okay? So what can we say? Therefore, we'll re-express it now. We've got our ticket to get rid of R out of that equation. V is 1/3 of H times, not R squared, but H over 3 all squared, times H. Now, let's just simplify that a bit. Heavens! V is pi H cubed over 27. How simple is that? I think I can VDH that, can't you? Definitely. It's pi H squared over 9. Wow! Okay, yes, that makes me smile too. Alright, I think we better go to the next screen. Now, yes, dv dt is what we know, dh dt is what we want, and dv dh is what we needed, but we now have. And that's where we resume our problem-solving exercise, so we can say that. That's what dv dt is. It's plus 2 centimetre cubed per second, and that's equal to our newly derived expression for dv dh, only in terms of h, and that's the dh dt which we have to find out. We're so close to the end now, it's quite exciting. So, therefore, yes, we're going to solve it for, we're just going to solve it for dh dt. And we'll be full of glee, you and me. Therefore, dh dt will be, I just rearranged that equation a bit, it's going to be 18 over pi h squared. But if you look back at the original question, they gave us a value of h. They said they wanted it to be 5 centimetres, okay? So we just plug that in now, plug and play. And dh dt will be that, which will be that. And put your correct units in, thank you Mr. Box. That'll be centimetres per second, okay? And just a word of caution there, if they started giving you flow rates in litres or something, look, don't mix the units up. Just convert those litres into cubic centimetres and all will be good. Otherwise, disaster is just around the corner. Alright, so congratulations for understanding that. And if you didn't, delayed congratulations when you go back and have another look at it, okay? Oh yes, what have you got to say for us, Mr. Smiley? We conquered the cone of death, didn't we? Yes, and we did it easily. Right, another one. What's this got to say? Well, we've got a radius of a circular disc which is increasing at the constant rate of 0.005 centimetres per second. Find the rate at which the area of the disc is increasing when the radius is 20 centimetres. All right, now look, let's just draw this thing up so we can see what we're talking about. That looks like, what a great diagram. Very good. So it's expanding. The circle's expanding, is it? Right. Then the radius is expanding. Okay, now this is the question. This is the question I want you to get used to asking. What rate do we know? The first of two questions. Well, I think we know the rate at which the radius is increasing, which would be dr dt, wouldn't it? Yeah, we know all that. That's r and that's a. So dr dt, yes, it's 0.005 centimetres per second. That's good. Now the second question was, do you remember? What rate do we want? What are they asking us for? Okay, well that rate is the rate at which the area is increasing, which is dr dt. Okay, now let's set up our equation now with dr dt, the one we know, on the left, and we're just going to write it like that. Dr d what? Dr d something times d something dt, and what goes in the blank? Well, it's what they ask us for. See the little red circle circling the A? That's what goes there. Now, we're done now. It's all just a matter of working out what to do now with that, because that is what we know, so there's nothing to do with that. That is what we want, so there's nothing to do with that at the moment until the end, and this is what we need. So the question is really about getting that thing. Now, do you know of a relationship between the area and the radius of a circle? Well, of course you do. A is pi r squared. You've been learning that forever. So, could you dAdr that thing? I think you could. 2 pi r. Now here's the twist, guys. We're not asked for dAdr, are we? No, we're asked for dr dA, and that is just the reciprocal. 1 over what we got above. Okay, that's perfectly valid to do that, okay? 1 over dAdr is dr dA, which is 1 over the right-hand side. So now, isn't that very fortuitous for us? So now, I think we've got everything we need now to solve this thing. Yes, I'm very happy too. Smiley, thanks. Oh, here we go. We're going to use this. We're back at the chain rule equation, and we're going to sub in now. So, we're saying that 0.005, which is dr dt, is equal to 1 over 2 pi r, which is, what was that thing again, dr dA, times dA dt, which we have to get. So let's just solve it now. We're going to solve it for dA dt, and we will be full of glee, you and me. And here it comes. Oh, isn't it beautiful? It's just absolutely so satisfying when you get to that point. Now we just have to, what value of r are we supposed to be using? Look back at the question, 20. Okay, here we go. And here it comes. Easy as pie for you and I. There you go. Wasn't that easy? So easy. Thanks, Mr. Box. Thank you so much, Mr. Box. Alright, so have we got any more? Oh, I've got another one. Heavens. Oh, gee, I'm working you hard today. Well, what have we got here? A diagram shows a block of ice. The dimensions are in centimetres, and we've got to do 3 things. Find an expression for the surface area, S, in terms of x, and then we've got to find ds dx in part B, and then part C, we've got ice is melting, so that S is decreasing at a rate of 4 cubic centimetres per second. Find the rate at which x is... Oh, there's your chain rule-y thing. There's the chain rule, guys. Well, first of all, we better sort out part A, the surface area. Alright, here we go. The surface area of this thing... Oh, let's do the front and the back, because it's a prism thing, you know, like, which has constant cross-sectional area all the way through it, so it's easy to work out these things. The front will be the same as the back because it's a prism. So what's that going to be, guys? 9x times x, which is going to be times 2 because there's a front and a back, which are the same as each other, and that gets us 18x squared. Okay, let's do now the surface area of the 2 sides, okay? What's that going to be? X times x is one side, times it by 2 gets you the 2 sides, and that comes to 2x squared. Good. Now, what have we got now? Surface area of the top and the bottom. Okay, easy. That's 9x times x for one of them, times 2, and that gets us 18x squared. Okay, do you agree with me? I think I'm right. Therefore, the total surface area is 18x squared from there, plus another 2x squared from there, and plus another 18x squared from there, and what's that add up to? 38x squared, no problem. So that's, is that the answer to... It is, Mr. Box? Oh, thank you, Mr. Box. Good, we've done part A, and we're gliding along. Okay, oh, look at that. Gee, that was easy. Part B, there was not much work in that. I just differentiated that thing in the box from part A to get 76x. Mr. Box, oh, he's working hard today. Now, that's A and B done. Here comes C. Now, C is the one where we've got to figure out what's going on here. We've got to set up our equation, right? So, now, okay, what rate do we know, guys? What rate did they give us? Yeah, they gave us the fact that S is decreasing at the rate of 4 square centimetres per second. So I think that means ds dt, don't you? Of course it does. Now, do you notice the minus 4? Because it's going down. Don't forget that minus. It's not going up, it's going down. So the rate of change is negative. Okay. Now, second question. What rate do we want? Well, they're asking us for the rate at which x is changing. So that means dx dt for you and me. And so that's all we need to do with that. Now, we can set up our equation now. So starting with ds dt equals ds d something times d something dt. What goes in the blank? That's what goes in the blank, the x. Oh, isn't it easy? Okay, so that's what we know. Don't have to do any work on that. That's what we want. That's so we don't do any work on that at the moment. But this one here is what we need. But hang on a minute. Have a look at part B. Oh my goodness. They basically helped us to work it out in anticipation of needing it now. So we don't have any work to do. Let's just sub in. Minus 4 was the minus 4 centimetres squared per second was the ds dt. That's going to equal 76x, which is ds dx, times dx dt, which is what we have to work out. So we can just start substituting or rearranging now, solving for dx dt. And what do we get? Dx dt is minus 4 over 76x. Oh, wow. And x is, look at the question in part C, 5. There it is. And just sub in, and what do we get? No problem. I think 4 and 76 have got a common factor. In fact, I think it's 4. It is. Okay, 4 goes into that 19 times, so that makes it really easy if you're in a tech-free exam. And 5 19s. Do you know how I multiply by 5? I just add a 0 and then divide by 2. So that's going to be 190 over 2, which is going to be 95. Voila, there you go, Mr. Box. Thank you. There's the answer, guys. Now, come on, that wasn't hard. It's not hard if you've got a bit of practice, but you know sometimes it's hard for people like me to know just how hard it is for you because you've never seen these before. So you know I don't want to underestimate the difficulty level. You'll only get good at them by practice. You know that's the thing. Not me just ranting on here. I'm just giving you the scaffolding to help you then put the flesh on the bones. That's what it's all about. Okay, now here's a. This one here is a very interesting question. It's not actually a related rates. It's actually a question which I've seen in an exam, but it's an interesting question because it's a bit tricky. You have to set up a relationship between R and H of that little cylinder you can see in that diagram. Anyway, look, I won't preempt it. I'll just go into it. But it isn't actually a related rates, but I want to show you how to do it anyway, in case, because this was where the cone of death name came from. Okay, so we're going to make the cone of death into the cone of easy. Right, a cylinder fits exactly into a right circular cone, so that the base of the cone, which is it's an upturned cone, so the base of the cone is actually at the top, and one end of the cylinder are in the same plane. So that means they're flush at the top. They're always even at the top. That cylinder doesn't poke out of the top of the base of the cone. It sits flush with the base of the cone. The height of the cone is 5 centimetres and the radius of the cone is 2, as shown. The radius of the cylinder is R and the height of the cylinder is H. So there's your R and there's your H, all right? Now what are we supposed to do? For the cylinder inscribed in the cone, that can change dimensions, guys. It can change dimensions. So if R gets smaller, then H is going to get deeper so that the cone sits flush in against the edge of the sloping sides of the cone, if you know what I mean. Now, we've got to find H in terms of R. Now look, similar triangles to the rescue, guys. There's a little purple triangle, and because that's an important triangle, and here's another one from the actual cone itself. Now I'll put them out. Yeah, that's there. Now that's important. See that? I've just labelled that side 2 minus R because that's what it is. Now you just see whether you agree with me. It is 2 minus R, isn't it? It is. So therefore, by similar triangles referring to the diagram, I can say that there's that little purple triangle, and here is the blue one, right? I've labelled the sides 2 minus R and H for the cylinder, referring back to that little purple triangle inside the cone diagram. Do you agree? Good. Now the blue one, that's going to be 2 and that's going to be 5. Now, those triangles are similar. They are similar. So therefore, 2 minus r over h, in other words, the horizontal over the vertical, will be the same. Will have the same ratio as in the blue triangle, the horizontal over the vertical in that triangle. Okay, so now we're set up, guys. We can just get h in terms of r easily. I'm going to cross multiply. 2h equals 5 times 2 minus r, or 10 minus 5r as shown. So I've just got to solve it now for h, which is so easy. I've just got to divide by 2. So therefore, h is 5 minus 5 over 2r, and Mr. Box is going to come and finish it off for us. Thank you, Mr. Box. And that's our relationship, everybody. That's our relationship. That's what we want. Now, that's the difficult part of this question. Many students got that wrong, I can tell you. They got it wrong because they probably panicked and didn't know how to do similar triangles. You can easily see that they're similar. They are similar because you've got, in both cases, you can see you've got a vertical and a horizontal line, therefore a right angle formed by them, and you've got, because the verticals are parallel, you're going to have that angle right down the bottom of each of those triangles. Shown on the right, they will be the same angle. Therefore, the third angle is the same as well, because all angles add up to 180. Therefore, they are equiangular, AAA, and therefore they're similar. They're just scale models of each other. So, but you don't have to prove that in exams. They just accept that that's all right, okay? That you can do that. Oh, goodness. What are we going to do now? Okay, here's some more stuff. This is part B and part C of the same question. The total surface area S of a cylinder of height h and radius r is given by the formula S is 2 pi r h plus 2 pi r squared. Find S in terms of r. Well, if you look at that formula above, that means we've got to get rid of h, because r has a relationship with h. It's a function of h, because we just found out that relationship in part A, which was this. So all I'm going to do there, guys, is I'm just going to plug h into that formula above and get rid of that and just put it in terms of r, because they want S in terms of r. Here we go. S is 2 pi r times, there's h in the bracket, plus 2 pi r squared. Now, all we've got to do now is just simplify that a bit. Those 2's will cross out, won't they? And what do we get? We get 10 pi r plus, minus, 5 pi r squared plus 2 pi r squared. Okay, so like terms there. Those second and third term are like terms, so just clean that up a bit. 10 pi r minus 3 pi r squared, and Mr. Box was very keen. Thank you, Mr. Box. That is the expression we need for S in terms of r. And the third part of the question, part C, says, find the value of r for which S is a maximum. Well, that's just basically a straight derivative question. So therefore, ds dr will be 0, and that's equal to, taking the derivative of the expression above us in the blue box, we get 10 pi minus 6 pi r, and therefore, when S is a maximum, ds dr will be 0, as we all know, and therefore we set it equal to 0 and solve it for r. And what do we get? We get that, and then we cross out the pi's, and then we get r will be 10 over 6, but that's not the end. Don't leave it like that or you'll lose your answer mark, because there's a very simple cancellation to do there, which will be 5 over 3, and that's the answer. There you go. Okay, so how did you enjoy all that? Related rates are now basically your mates, not your hates. Okay, if you didn't get some of it, just go over it and have a look at it again. But the most important thing is for you to practice. Just practice it, and you'll just be an expert at it before very long at all. Okay, enough from me. Thanks very much for listening, and we'll see you next time. Bye.